Okay, 2012 AMC. This was problem 22 from the AMC12A, and it says distinct planes, P1, P2, all the way up to PK, intersect the interior of a cube Q. Okay, that's important. Let S be the union of the faces of Q. And let P equal the union of all K planes. The intersection of all of the planes and S consists of the union of all segments joining the midpoints of every pair of edges belonging to the same face of Q. What is the difference between the maximum and minimum possible values of K? And actually, this problem wasn't too hard. I'll draw a few things here, and I'll actually show you a nice 3D diagram that, of course, we wouldn't be able to use on the test. But here's the idea. So one face of this cube, what it's asking for is the planes that cut into this face must intersect all of the segments connecting the midpoints of these. Okay, and of course there are so they are going to be 1, 2, 3, 4, 5. So on here, 1, 2, 3, 4, 5, 6 total. So 6 segments per face and 6 faces. So basically I need to make sure that I intersect the cube along 36 segments with planes. Okay, and I'll show you everything nicely in a second, but basically the most possible ways that I can intersect the plane is so a plane can intersect a cube and hit at most 6 segments. So we have at most 6 segments per plane. So the smallest number, so the minimum must be greater than or equal to 6. It's actually going to equal 7. We'll see that shortly. And then we need to figure out how we can get as many planes as possible that go through the interior. They have to intersect the cube, but only intersect along here. So now let's go, and I apologize for the clicky mouse, but it's easier to use this program with that. And we see a cube. And for the minimum number, I told you we'd have we would have the maximum number of segments that a single plane can intersect is 6. So this plane right here, you can see it clearly intersects in 6 of those segments we needed, taking care of 6 of them. Okay, and for that, I'm going to use 4 of those planes, and basically, so it's hard to describe, but you can visually see it. Basically, I'll have one plane that will cut off each of these corners of the face, and so 1, 2, 3. It's hard to see that one because we're looking dead on at it. 4. So I have those 4. And I also can have these sort of vertical, horizontal, and other vertical planes that cut off 4 faces. But notice these only cut off 4, so I need 3 of them. As you can see, that one, and that one. And these 7 planes I just showed you, that, 2, 3, 4, 5, 6, 7, are the plane's minimum number of planes needed to get every one of those so segments. So the minimum is actually equal to 7. Now we just need to find the maximum, and then we'll be done. So the maximum, well, basically there are only a few types of planes that can intersect this, and let me describe it with the clicking mouse and with this up here. So we have those 7 planes we saw before that cut the cube in half in various ways, okay? Down, parallel to faces, or cutting through 6 segments. And we saw those, so planes like this, there are 3, and there are 3 or 4 planes like this. But we also have planes that cut off one edge, as you can see, like this. And since there are 12 edges on the cube, there are 12 of these such planes. I'll show you those shortly. Or I'll show you right now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 1 for each edge. And I can also have the planes that will cut off one corner at a time, like this. Okay, you can see it's cutting off this close corner. And since there are 8 corners in a cube, there will be 8 such planes on this. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's just go back and see what we have. So the maximum number that we have, well, we had the 3 planes that were the horizontal and vertical planes. We had the 4 planes that cut through the middle with 6. We have the planes that cut off the edges. There are 12 edges. And we have the planes that cut off the corners. There are 8 corners. So there are a total of 27 planes that I can get to, different planes that I can get to intersect the cube only along these segments at the edges. And so 27 minus 7. 27 minus 7 equals 20. Answer is C.